Lakers. This video is to help support this week's CK12 lesson, which is about geometric sequences. Geometric sequences are just an extension of exponential functions. They behave in the same way, they're just modeled slightly different. So let's take a look. At the beginning of the lesson in CK12, it asks you reminds you how to shift functions. So please refer back to this idea back when we started chapter 5. This would have been the start of third quarter. And this represents how we shift things in a function. This value outside, highlighters out here, this value outside, this k, tells us we'll go up or down. And then this value h, I'm going to highlight in green, tells us to go left or right. Notice that if h is negative, say we go -4, oh, that should be a plus. Not +4, that should be a plus. But notice a -5 tells us 5 units to the right. So this part is correct. Okay. It's kind of the opposite of what you might think. And if you need some reminders, I would encourage you to maybe pause this video and practice putting these functions into the graphing calculator. Okay. When we look at these types of shifts, here are the transformed functions. Notice this x squared function. We're going to move to the right 5 and up 3. Well, right 5, that means -5. Up 3, a +3 on the outside of that squaring term. Notice here we're going down 2, so we're subtracting 2. And then looking at part C, we're going to go down 1 and we're going to go left 1. So notice the left is represented by +1. And then the down, of course, that is intuitive. It is -1. Feel free to look at those and type those into the graphing calculator, and you can see the transformation from one function to the next. Same with these. Again, feel free to go to the graphing calculator. These are the transformed functions. Feel free to pause the video and think about how just those horizontal shifts are affected with the x value, all with the x term. Okay, then let's talk about Steph and James. They both play basketball, and the rate of their points that are accumulated in the season are different. One models with a linear function, and the other one is exponential. James doubles the amount of points that he obtains every game, where Steph, he gains 4 every game. But he starts out great, and James starts out low, but we'll see in the end that James will grow faster. So the next couple slides just talk about where those equations are coming from, and then talks about the different y-intercepts, and also talks about a limit. Because at some point, James's scores are going to be out of hand and not really realistic. 8th game, 768 points. We know that is not possible in basketball. Then there are a couple progress questions, and I'd encourage you to look at the graph to help you answer them. So that first one, and then the second one. Here's the third one. Remember those shifts. So because they started 5 games into the season, that means that their their models are shifted 5 spaces to the right. And again, here's Steph's. And then it gets into some ideas where what is the domain? In other words, what x values? How many games are actually played? Well, because they didn't start until the 5th game, Maybe they were in quarantine. They didn't start to the 5th game. They only have total 4 games in their season. The next one is true or false. Steph and James don't start playing games until game 5, and James will eventually surpass Steph's score. And you can see from the table that that is wrong. Steph is still 6 points ahead, or I'm sorry, 8 points ahead of James at that 8th game. Now we get into some exponential versus, geometric versus arithmetic sequences. So on the left, here we have arithmetic. On the right, we have geometric. And geometric is just another way to represent exponential functions. So you're multiplying a number to get the next term. Here's another one asking you for how many points will he score in his first game? Well, because LeBron missed that preseason game, he's starting in the first game, the scores that he would normally get in the preseason game become his first game. So that's why it's 5. Here is another example. Notice that there's 3 models that represent the number of points that he will have in the 6th game. Here is how we define sequences. Remember, this is linear right here. Also known as arithmetic sequence. And then, second one we know as exponential. Which is a geometric sequence. So let's focus on the geometric sequence for a moment. Here's the geometric sequence model. So we can find any term in the sequence using the first one and this common ratio. You might also know it as a common multiplier. And then we base it on the first term instead of the 0 term in an exponential function. So if we have that first term, we have to subtract 1 because we already have the first. So then we keep moving forward from there. So this n tells us how many numbers are in the sequence, how many terms. So let's take a look at an example. Here we have a sequence, and it is a geometric sequence. And we know this because what do we multiply by 5 to get 15? 3. What do we multiply 15 by to get 45? 3. And it keeps going. 45 times 3 is 135. 135 times 3 is 405. And it would keep going in that same pattern. So what that multiplied by 3 is our rate of growth. That's the common ratio. We know what our first term is, that's 5. And so what we want to do is write an equation for the sequence using sequence notation. So here we go. Start with the first term and that common ratio, which is 3. Here's the division to show that the value between each consecutive term is a multiple of 3. Here is how we write in sequence notation. And then plugging the values in. 5 is that first term, 3 is our common ratio. Here are a couple other progress problems that walk you through that same idea. I'm going to give you a heads up on the third one here. Placing these 5 boxes into their appropriate place took me some time. It just wasn't being cooperative. So if you get stuck and you know that you're correct, just move on and feel free to look at the last couple examples from this slide or video, and don't worry about submitting it in the actual lesson. Here's 4 and 5. Notice that this is not arithmetic because you have to multiply 4 by 3 to get 12. Multiply 12 by 3 to get 36. Multiply 36 by 3 to get 108. Here is a summary of what the different sequences look like. Again, focus on the exponential. Here are two questions from the progress. The first two are arithmetic sequences. Feel free to just skip through them. And then here is 3 and 4. This one also represents an arithmetic. Okay, so here's a problem that comes up commonly on IB tests, where you know one of the terms in the sequence and you know another random term in the sequence. And what we have to do is find the common ratio. That's what our goal is. So we know the second and the fifth term. And so how many times do we have to multiply the second term to get the fifth term? Well, that means we're going to multiply it 3 times. From the second term here's the third, here's the fourth, here's the fifth. So we're going to have a total of 3 terms between 3 multiplications between the second and the fifth term. And so that's why it's the second term times r to the third power. Well, when we do a little simplification, that r third value is just the fifth term divided by the second term. And so we get r cubed is equal to 343. Now, in the attendance today, you should have looked at a video of how to find the cubed root of 343. So that's what you would do in your calculator, and you get 7. And so there is our common ratio. Well, how do we get the first term? Well, we know the second term, and we know what we multiplied by. So we take that second term and divide it by 7. That becomes the first term. So the first term is 2. So we found our information. Let's check our answer and verify it. Yep. Common ratio or common multiplier is 7. Ratio is 2. Here's what that cubed root of 343 looks like on the calculator. Here's another couple examples. Again, don't worry about A or B. Those are arithmetic sequences. Focus on the geometric. Notice that the common ratio is bigger than 1, and so that is an example of growth. And this last one, it's a mountain of dirt eroding in the rain. Notice that this is decay, eroding. It is going down. Now, these multipliers are easily found by looking at the information. Here we see that word double. And so that's why we see growth and we're at 2. And then similarly, it says that the height of it is half. And so that's why the constant multiplier is half. Another work it out question asks us to identify whether it's arithmetic or geometric, and then write, find the common ratio. So if we just focus on B and E, notice D, I think, definitely is neither. There's a pattern. I would say 26 and 27 are the next numbers, and then there's a B, another 5. If you agree with me, then that's definitely neither. If it's something else, then they made a typo. You decide. So when we look at B, notice the first term is 2, and then we go to 6. Well, 2 times what gives us 6? 6 times what gives us 18? We see that as 3. So the common ratio is 3. And so here is the model for part B. It doesn't ask you for that model, but I encourage you to try to build those models whenever you can. In the last one, we see 10 and then 15, 22 and a half. We divide backwards, we get 1.5. First term is 10, and so here is our model. Next, there's some that are arithmetic. Any of the sequences that are geometric, they either want you to write the explicit formula or the recursive formula. The recursive formula is D. In parts C and E, those are the explicit. So I will highlight those as such. So the explicit, that's C and D, but then we've got this recursive, it's D. Just two different ways to represent it. Here's another example where, again, we have the fourth term and we have the fifth term, and we're asked to write a model. So look at the progress. You take the fifth, divide it by the fourth, and you get 1.5. And if they're consecutive terms, then we don't need to take square roots or any other roots. Then we have to work backwards to find the first term, and then use that first term and the common ratio in the model. There's a couple other examples to follow. Feel free to pause and review as you like. Here's another example from the progress, but again, you're given the fourth term, you're given the seventh term, you've got to find the ratio and even try to build the model. Here's another one with the fifth and the ninth. Well, how many multiplications are in between the fifth and the ninth? 4. So you're going to end up having to take the fourth root at the end to find that multiplier or the common ratio. There's a couple other examples. Feel free to look at those on your own. They're getting you to the same idea. One more. And then here's a work it out example where you have the fifth and the seventh term. And so you're going to have 2 multiplications in between. So you're going to end up having to take the square root to find your ratio. Here's another summary. And then we get into the practice. So that concludes the lesson for today. I will put a separate video for the adaptive practice.